Today we're going to talk about the amplifier and the attenuator. The language we use to talk about them is the decibel. To get us started, let's do a quick math review. Remember, log base b of m times n is log base b of m plus log base b of n. We see that this multiplication has become an addition. Here's an example. We'll take the log base 10 of 10 times 3. We can rewrite that as log of 10 plus log of 3. Go into the calculator, that's log 10, which should equal 1. So that equals 1 plus log 3, which is 0.477. So together it's 1.477. We could just as easily have said the log of 30. Once again, we find the same answer, 1.477. Once again, a multiplication becomes an addition. Also remember that log base b of m divided by n is equal to log base b of m minus log base b of n. In this case, a division becomes a subtraction. Here's an example. The log of 1 over 30 is equal to log, again we're using base 10 because there's no subscript here, so log of 1 minus log of 30. The log of 1 is 0. You can prove that to yourself over here if you calculate if you like. So the log of, that's the log of 1, there we go, is equal to 0 minus the log of 30. So that's 1.477. So when we're done, that's negative 1.477. Again, a division has become a subtraction. Do make sure those log properties are on your note card. We will certainly come back to them in a moment. The amplifier. The symbol for the amplifier is a triangle. We're going to put an A in the middle of that triangle. We'll talk about the voltage in, the voltage out, and that A that we sketched in there will be the amplifier gain. The equation describing the gain of the amplifier is gain voltage is equal to voltage out over voltage in, with the assumption, with the huge assumption, that this amplifier is linear. What we just described is a voltage amplifier. We can also have a current amplifier. Same triangle, same A for gain, except this time it's power in over power out. The equation is the gain for power is power out over power in. We will call that a power amplifier. Notice that the gain in both cases is a relative number, describing the difference between the output power and the input power. Here's an example. Let the amplifier have a gain of 10,000 and let the power output equal 10 watts. So gain is equal to power out over power in. And we know we're talking about a power amplifier because our power output was specified in watts. To solve this problem, we substitute in our numbers. So the gain we said was 10,000 is equal to the power out, that's 10 watts, over the power in. Solving for power in, that would be 10 divided by 10,000. So we would describe that as 1 milliwatt. Notice that there are no units associated with gain. We can see why by coming to our definition. So gain is equal to power out over power in. For this particular problem, our power in was 10 watts, and our output was 0.001 watts. Dimensional analysis will tell us that the watts cancel, so you're left with gain as a unitless number. Our next item is the attenuator. You've played with attenuators before, back in electronics class. They looked like this. There was an R1 and an R2, such that you had voltage in and voltage out. You may even remember the equation as voltage out is equal to an R2, by the way, that's R2 there, over R1 plus R2, all multiplied by V in. When we rearrange the numbers, we can see that voltage out divided by voltage in is equal to an R2 over an R1 plus R2. Or if you wanted to simplify that, you could just say that the gain is equal to voltage out over voltage in. That term gain is arguably a misnomer. However, I think you'll allow it if we make the stipulation that 0 is less than or equal to the gain of the attenuator is less than or equal to 1. So the best you could have is a voltage output that's equal to voltage input when the attenuator has no attenuation, or you would have 0 output when the voltage output goes to 0. As a sidebar, you remember our communications model where we talked about the transmitter and we talked about a receiver? And for now, we'll assume antennas. It's the thing that's between them that I wanted to talk to you about. It's the channel. The channel will have attenuation. It doesn't matter what that channel is, it will still have attenuation. If it's over the air, there will be a certain loss. You'll have a very powerful transmitter, yet the receiver will pick up a greatly attenuated signal. There's attenuation if it's a cable. There's even attenuation in fiber optics. With that in mind, we go back here where we talked about amplifiers and attenuators, and we can put them together. For example, we'll let this first amplifier have a gain of 100. So amplifier 1 with a gain of 100. We'll let this attenuator have a gain of 1 over 20. Yes, I realize it's an attenuator and we're describing it as having a gain, but you can see that the output would be smaller than the input. Finally, we have amplifier 3 that has a gain of 5. Regarding this attenuator, if it helps, you could think of it having a loss of 20. The total gain is calculated as 100 by 1 over 20 by 5. So the total gain is equal to 25. Remember, there are no units associated with the gain. To see how this works, let's assume there's a 1 volt input into the amplifier. The output of the first amplifier would be that input multiplied by 100. We enter the attenuator, that signal gets divided by 20. So the output would be 5 volts. The second amplifier is going to multiply that 5 volts by 5, giving us 25 volts out. So if we took the entire amplifier chain, we could sketch that as a single amplifier with a gain of 25. 1 volt in, 25 volts out. Here's another example. This time we have 4 stages, and we have gains of 10, 0.4, 20, and 0.6. Final thing is we'll assume the output voltage is equal to 1 volt. Our objective is to find V in. We'll start by sketching a picture. Because it has a gain of 10, gain 1 is equal to 10, that is an amplifier. The second device is an attenuator. We'll sketch that as a resistor. So gain 2 is equal to 0.4. Next is another amplifier with a gain of 20, and that's followed by another attenuator with a gain of 0.6. And we're also told that voltage out is equal to 1 volt. For this cascade of devices, gain total is equal to 10 by 0.4 by 20 by 0.6, giving a total gain of, so it's a total gain of 48. Redrawing the circuit, gain total is equal to 48. Our output voltage is equal to 1. What is V in? Gain is equal to voltage out over voltage in. So our voltage in is equal to V out divided by the gain. Our voltage out is 1 volt divided by 48. So our voltage in is 1 over 48 volts. Here's another example. This time we have a transmitter. Like all transmitters, it has a modulator. And we'll let this particular transmitter have a power output of 10,000 watts. That signal goes over the air to a receiving antenna. The receiver has a demodulator. For this example, the loss is given as 3.6 times 10 to the 12th power. We have a transmitter, a receiver. We're told the output power, and we're told the loss. So the thing we must be looking for is what is the receive power. When we sketch that system, we get something that looks like this. We start with the attenuator, which in this case, we're showing the channel. Again, the channel that has a loss of 3.6 times 10 to the 12th. Our power input is 10 kW. Again, we are modeling the channel right here. And our power output, which is the input to the receiver, is what we're looking for. So that is the unknown. The loss of this attenuator is 3.6 times 10 to the 12, which means the gain is equal to 1 over the loss. Another way of saying that is that the output power is going to be the input power divided by this loss. Using our gain equations, we see that that's equal to power out over power in. Solving for power out, that's gain by power in. In this case, it's 1 over 3.6 times 10 to the 12 by 10,000. So our output power is 3.6 E12. We'll take the inverse of that, multiplied by 10,000. The result is 3.8, and because it's 10 to the negative 9th, that would be nanowatts. So if we go back to our original drawing, we would see that the power at the receiver is 3.8 nanowatts. One thing you'll notice is that these radio problems have tremendous differences in their numbers. Here you have 10,000 watts, and here you have nanowatts. And I suspect you've never worked a problem that had such a magnitude of difference in numbers before. Wouldn't it be nice if we had a convenient way of expressing both very large and very small numbers? And it turns out we do. And I think you know where we're headed. We're going to logarithms. We're going to describe decibels. While your note card is out, go ahead and write this down. We're going to talk about decibels. The definition for voltage is 20 by log base 10 of voltage out divided by voltage in. If we're talking about current, the decibels for current is 20 log base 10 of the current out by the current in. And finally, if we're talking about power, the equation is 10 log base 10 of power out over power in. For this class, we're going to concern ourselves with voltage, expressed in decibels, and power, expressed in decibels. To understand decibels and how they're applied in radio work, we're going to revisit each of our previous examples. The first was an amplifier with a gain of 10,000 and a power output of 10 watts. The decibel gain of this amplifier is 10 log of 10,000. To see where that 10,000 came from, we have to go back and we have to make a slight adjustment to these equations. For voltage, the decibel gain is equal to 20 log of voltage out over voltage in. That's the same as saying 20 log of the gain of the amplifier. Same thing for power. The decibel gain for power is 10 log of the power gain of the amplifier. Back to our example, now you can see where that 10,000 came from. Using the calculator, 10 times log of 10,000 is equal to 40. So the gain of this amplifier is 40 dB. Next, we consider an attenuator. Power in is equal to 10 watts, and power out is equal to 0.5 watts. The decibel gain is equal to 10 log of 0.5 divided by 10. That might seem backwards, but let's look at it this way. So our power in was 10 watts and our power out was 0.5 watts. Power out goes on top. So if we go back up here, it was power out in the numerator and power in the denominator. Using the calculator, that's 10 times log base 10 of 0.5 divided by 10. So the gain is equal to negative 13 dB. We better make a note so we remember this property. For attenuators, gain is negative, which is different than linear gain, where the gain was always between 0 and 1. For this particular problem, the linear gain would have been 0.5 divided by 10, which means a gain of 1/20th linear is equal to negative 13 dB. Again, linear, and then this is dB. Here's another example. This is our multiple amplifier attenuator example. Gain 1 was 10, gain 2 was 0.4, gain 3 was 20, and gain 4 was 0.6. And our output voltage was equal to 1 volt. Since we're dealing with voltage, gain 1 in decibels is 20 log of 10. 20 times log 10. So that's just 20. Gain 2 is equal to 20 log of 0.4. That's negative 7.96. Gain 3 is 20 log of 20. 20 log 20. So that's 26.02. And finally, gain 4 is 20 log of 0.6. 20 times log 0.6. Negative 4.44. So if we sketch that up here, we could say the gain is 20 dB. The gain for the attenuator is actually negative, so negative 7.96 dB. The gain for the amplifier here, 26.02 dB. And the last attenuator is negative 4.44 dB. from our log properties, we made it a point to say that multiplication becomes addition. So in yellow, you remember we multiplied all of these together, right? When we did it first time, it was 10 times 0.4 times 20 times 0.6. Right, so we talked about a linear gain. We'll write that here as linear gain is equal to 48. Once again, for linear gain, we were dealing with a multiplication operation. For decibels, it's an addition. So we take all these numbers and we add them together. That gain is 20 minus 7.96 plus 26.02 minus 4.44, which is 33.6 dB. The linear gain is 48. The gain expressed in decibels is 33.6. We can convince ourselves of that by going back to our base equations. So the voltage gain in decibels is 20 log of power out over power in. We also said that gain is equal to power out over power in. So we can rewrite this as 20 log of the voltage gain. So the gain in decibels is 20 log of 48. Let's see if that works out. So 20 times log 48 is 33.6. So the gain is equal, go back to green here. So the gain is equal to 33.6 dB. And one more time, that means that this, talking about a system with 48, again where this is V in and V out, is equivalent to saying this. V in, V out, 33.6 dB. Same thing. If we go back to the beginning, we talked about a voltage output of 1 volt. So let's move that down here. So V out is 1 volt. Same over here. On the linear side, we say gain is equal to voltage out over voltage in. That's 48 is the gain, is equal to 1 over V in. Therefore, the input voltage is equal to 1 over 48. With the dB calculations, we said gain in dB is equal to 20 log of V out over V in. 33.6 is equal to 20 log of 1 over V in. So we divide this by 20. So that's 1.68 is equal to the log of 1 minus the log of V in. I believe the log of 1 base 10 is going to be 0. So that's 1.68 is equal to negative log of V in. Let's shift that negative over to this side of the equation. And now we need to break voltage in out of jail. And the way we do that is we run it through the star off machine. To do that, we take 10 and we raise it to negative 1.68. And we take 10 and we raise it to the log base 10 of voltage in. Now we have voltage in is equal to 10 raised to the negative 1.68. So our voltage in is 0.02. And that should be very close to 1 over 48. There we are. So we can come over here and we can say voltage in is equal to 0.02. So there you go. You can see that both methods yield the same results. Next is that radio transmitter problem. Here is our transmitting antenna. So power out for that particular transmitter is 10,000 watts. That antenna goes over the air to a radio. And we were told that there's a loss of 3.6 times 10 to the 12th power. Our opening move is to put our channel loss into dB form. So that's 10, because we're dealing with power. So 10 log of 1 over 3.6 times 10 to the 12th. That's 10 times log, be really careful with your parentheses here, of 3.6 E12 pren invert last pren. The resulting gain is a loss, which is a negative dB, of 126 dB. Using our equations, we would say that dB is equal to 10 log, because we're dealing with power, so 10 log of power out over power in. Except in this case, we're talking about the channel. So this piece here is modeled as a resistor, and we talk about the power in to the channel and the power out of the channel. And it just so happens that power in to the channel is the output power of the transmitter, and the power out of the channel happens to be the power in for the receiver. So that arguably gets a little bit complicated, but just remember, you're talking about the channel. It's power into the channel and power out of the channel. So negative 126 is equal to 10 log of the power out over 10,000 watts going into the channel. So negative 12.6 is equal to the log of power out minus the log of 10,000. The log of 10,000 is 4. That makes this negative 8.6 equal to log of power out. To break this piece out of the log jail, you go 10 to the negative 8.6 is equal to power out, and solving, so that's 10 raised to the negative 8.6, which is 2.5, and that would be millimicro nanowatts, which is very close to our original linear calculation. We're in chapter number 2 of the textbook. We are learning the language of radio. Every discipline, it doesn't matter what discipline you choose, but every discipline has a language that's associated with it. It's a language that allows that discipline to talk about very particular things using a shorthand notation. The phasors that we learned in the previous class is an excellent example. The phasor was a shorthand notation, And once you learned how it worked, you were able to do a large variety of problems very quickly. But you remember what it was like when you first learned about phasors. It was a nightmare because it made no sense. Why would you talk about trigonometry in relation to AC waveforms? What we're going to do now is very similar to that experience with phasors. We are going to learn what it means to compare something using decibels. We're going to talk about dBW and dBm. This is the language that's used to express and measure our radio signals. For example, a spectrum analyzer, which we'll talk about in the next lecture and in lab, will express things in dBW. It goes something like this. Here is our amplifier. Power in and power out. When we talked about the linear gain, we said the gain is equal to power out over power in. You remember I said there were no units associated with that because it's a ratio. It's this compared to that. When we did the logarithmic form, it was the same story. The gain in decibels was 10 log of power out over power in. Once again, it's a ratio. It's this compared to that. It's output compared to input. Again, this compared to that. There's always a relationship. Now watch this. Our transmitting antenna has an absolute output of, say, 10,000 watts. All right, 10,000 watts leaves the transmitting antenna and goes over the air. We can express that power out relative to a standard. One of the common reference standards is the milliwatt. When we compare the transmitter output power, in this case 10,000 watts, to our standard, it looks like this. We would say the decibels relative to a milliwatt, so subscript m, is equal to 10 log of the power divided by 1 milliwatt. And you'll notice it's a ratio. We're always comparing this to that. Over here, once again, we compared output to input. In this case, we're going to compare some transmitter or some receiver power value to the standard. So it's this compared to 1 milliwatt. So the dBm for our 10,000 watt transmitter, whoops, that's 0.001, there we go. Now we wouldn't say gain, we would say power is equal to 10 times log of 10,000 divided by 0.001. So the power of that transmitter is 70 dB relative to the milliwatt. Here's a story for you. I had a mentor who would talk this way. The students would come in and they'd ask questions, and he would proceed to give them the answer. But he usually didn't stop there. He would talk about the answer, then he would talk about how the answer fits in with the rest of the discussions, and then he would talk about where you could go next, and then he would talk about stories that he had encountered personally when it came to that particular problem. When he was about halfway through, he would stop and say, well, fine, I'm giving you an answer that's about 20 dB hotter than what you asked for. In that particular case, the student came in asking questions and wanted to get this much material. But the professor would give them not only that much material, but about this much more. So instead of getting 1 unit, the reference, they received 20 dB more than the reference that they asked for. We may as well finish out the story by seeing what the professor really meant. So that's 20 is equal to 10 log of the information that the professor gave over the information the student wanted. So we'll talk about this being the professor and this being 1 unit for what the student wanted. So that's 2 is equal to log of what the professor gave minus log of 1, which is what the student wanted. This goes to 0. To break this p out of jail, we would say the professor actually gave the student 10 squared, or about 100 times more information than they actually wanted to know. That's something to keep in mind. These logarithms grow really, really fast, and you don't want your professor giving you 20 dB more than what you wanted. That's a long video. Goodness. Okay, so here we are. We're talking about 70 dB relative to a milliwatt. Let's look at a few more examples. For your Wi-Fi, if you have negative 50 dBm, you could consider that a reasonably good signal strength. How many watts is that? Decibels relative to a milliwatt is 10 log of the power of interest relative to or divided by 1 milliwatt. We sub in our values. That's negative 50 is equal to 10 log of P over 0.001. Negative 5 is equal to log of P minus log of 0.001. I believe this goes to negative 3. That's log of 0.001. Yep, negative 3. You got to watch your algebra now, because this is a negative and that's a negative. So that means we have positive 3 on the right side. We have positive 3 on the right side. We got to drag it over. So this becomes negative 8 is equal to log of P. Breaking P out of this logarithmic jail, we would say power is equal to 10 to the negative 8th power, which is the same as saying 1 times 10 to the negative 8th. If we move that to engineering units, power is equal to, let's see, we need to move this one more position over, so that'd be 10 times 10 to the negative 9, which is the same way as saying 10 nanowatts. Do be careful with your units. You'll notice there's watts here, and when we put this back into the original case, there has to be watts here as well, so that they can cancel out. And while we're here, just to make sure that we did indeed solve the problem correctly, we can say 10 times log of, let's see, 10 nanowatts, so 10 E, oops, not answer, let's try that again, 10 E negative 9 divided by, and then it was 1 milliwatt, so 1 E negative 3, and that better equal 50, or negative 50, as it does. We said every discipline has its own unique language, a language that makes things easier to describe. And now we can look at how all this decibel business would actually make things simpler. It makes things simpler because if you express your power in dBm or dBW, and you express your amplifier gain and your attenuator gain in decibels, all you have to do is add them together. For example, back to our transmitter, we said that the transmitter had 10,000 watts. And we worked that out to be 70 dBm. We talked about the attenuation of the channel. Now to figure out the power of the receiver, which is the output of this particular channel, is equal to 70 dBm minus 126 dB. So that's 70 minus 126. It's negative 56 dBm. You can see that that's about correct by comparing it to your previous answers. So negative 56 is equal to 10 log of the power going to the receiver divided by 0.001, so there's your 1 milliwatt. So 5.6 is equal to the log of power receiver minus the log of 0.001. We already know that goes to negative 3. So let's see, we've got a negative and a negative. We drag that over here. That becomes negative 8.6 is equal to log of the power of the receiver. Breaking this power out of jail, the power of the receiver is equal to 10 raised to the negative 8.6. And that works out to about 2.5 nanowatts, which is exactly what we determined in our previous solutions. If you were really paying attention, you would notice that this equation is peculiar. You would have noticed that we are adding, or in this case subtracting, dB from dBm. Yet you know the answer comes out as expected. Because this video is getting long, I'm simply going to stop. And I'm going to say that the answer to that question is about 3 dB hotter than any of us wants to deal with right now. And with that said, maybe we'll deal with it when we come back next time.